it earlier. Um, Relatively speaking, in terms of number of cycle, it obviously is a log scale here, so you have to use your own judgment. But the idea is that when people talk about fatigue, we tend to be idealistic, so everything I'm showing you right now is I'm always applying the same load up and down. Yes?
What actually causes that curve to bottom out at the first work hardening?
Well, so you have some work hardening in steel, and that's why a lot of times steel is said to have an endurance limit. Although there are some steels, especially if they're welded, that after it's flattening out, they're going to have another failure curve at 10 to the 9 cycles. So there's nothing that in all of this, and we're going to talk about polymer in the next class, there's nothing that's really absolute. You get away from one way of initiating a crack around a particle. Essentially, you can think of the endurance limit as a condition where the stress near all the little impurities in the steel are still at a level that doesn't create too much plasticity locally. Because what happens if you think of the material, that's probably a good way to address this. Yeah, that's good spot here. If you're looking at a material and say, well, so I have a yield strain, and that's when I run my stress strain curve. You know you have impurities in it. So at the impurity, if you take it as a sphere, you have a stress riser of 3. As soon as you reach 33% of your yield strength, locally you're yielding. If you're yielding just a little bit and have enough strain hardening, it's going to become elastic again. And that's what happens sometimes with steel. So that's why it heals itself. You stop the plasticity in these cycles, and then you can continue to stretch the bonds up and down. You have very little movement of dislocation. It's just stretching the bonds, even in the area of impurities. And that's why you don't have an overall effect. And it's just going to survive essentially an infinite number of loading, unless you have another phenomena in gigacycle fatigue that now initiate cracks in other ways. So at least you're safe with what is more common. With aluminum alloy, probably the easiest way to think about it here is, I told you there are more slip systems. So it's very hard to think of the aluminum alloy just completely losing the deformation. It's going to harden, but there's always going to be some deformation taking place. And therefore, you probably have to go to maybe, instead of being 40% of the yield strength, you have to go to 30% of the yield strength, which is what the math tells us, until you really don't have anything going on in terms of back and forth plasticity. The back and forth plasticity is really what kills the material in terms of growing voids. If you can stay elastic locally, then you're fine. That brings me to my example here with this turbine blade. So we've done some stress analysis looking into the area here, and it had to be elastic, even though it's a stress riser. This is the highest stress you had in the blade. It was the leading edge. So this mounts into the rotor here, and what I'm showing is essentially kind of some important contact points. We didn't have all of that all figured out, but we were really trying to look at the effect of changing this radius here. And because you have a very nice surface finish, and some of them can be single crystals, you can go a little beyond that 40% of yield strength that we talked about, but not a whole lot, because eventually you would start a crack. It's just going to take longer. And that's why you limit the life of these components by saying, okay, it's been 5,000 hours. I don't remember. It depends on the frequency and stuff. But if it's considered a stress life, typically at 10 to the 6 cycles, is an area where you can retire it, and you anticipate if you were to keep it, that it will continue to work fine for another period of time. And one of the biggest issue here with making this type of analysis is you don't know exactly your stress level, because all has to do with the dynamic in the engine. You can instrument some of it, but I wouldn't put a strain gauge there and try to run it. So there are some limitations as to how precisely you know your stress. At the same time, when you run a material test, I'm showing here some curves from, it was a reverse engineering. We were trying to figure out if this would work to change manufacturer for the turbine blade. You have variation. So this is the same, we're looking at stress level and number of cycle to fail. So here we had some that fail in 5, so that's 200,000 cycle all the way past 5 million cycle for almost the same loading level. And it's just part of either changes in surface roughness or some variation in the microstructure. These were just tensile specimen, and what I found from experience in running these high cycle fatigue is if in the whole section there's one particle that's larger, that's where the crack's going to end up. So it becomes a little bit more like a ceramic. On a ceramic, that's very notorious. You're looking at the largest porosity, that's where the crack's going to start. Doesn't matter if you have 1,000 of them, you only need one in one area. Obviously, if you have 1,000, chances are you're going to have two next to each other, so that makes a bigger one. But here the idea is you're looking at a large volume of material, and the biggest impurity on one sample is going to be different than the biggest impurity in the next sample. Because these are outliers. They're things that you like to avoid, you just can't. So I would really, for you guys, it's something to really take in mind as far as depending what you design, you may have something other than air as far as the environment, and that can lead to the stress corrosion cracking if you have chlorides and those sorts of things. So they're just really constraints in your design. If I know I'm going to have high chlorides and a lot of sustained load, and I need things to be very reliable, ceilings of swimming pools, stuff like that, you need to avoid that stress corrosion cracking. You may as well use regular steel that will rust and maybe eventually drip rust through the ceiling, then put something that will look fine and then all of a sudden break one day. That's one example. Just all the building structures. The aircraft, what happened is, depending on the alloy you use, you have a lot of variation in that stress corrosion cracking resistance, because the alloys affect the stability of the little oxide here that we were talking about. Where did we talk about that one? Yeah, I think it was right here. So I just mentioned that you were going to have that little protective film. So the alloying element, other than aluminum, magnesium, copper will have some influence. They're all going to affect the chemistry of what's going on in that crack tip. So there are some chemistries that you can almost avoid the stress corrosion cracking, but then you don't have all the straightening benefits. So it's always ends up as a compromise. The fatigue is slightly different. Every material will fatigue. So it's not a black and white figure. At the same time, you can think of it as being a little easier to predict. If you have a lot of cycles and you're looking into comparing like endurance limits, so stress level that you can have for the endurance limit is 10 to the 8 normally, but the fatigue limit we call is 10 to the 7 cycles. So you can compare material at that level and see some differences. keeping in mind then their purity is going to influence that curve, because you're looking at the largest flaw where the crack is going to initiate. And that's why in aluminum alloy, there's some special grades that have less iron, less impurities in general, that will increase that fatigue characteristic. If it's something that you care about, it could be that the problem is stress corrosion cracking, and it doesn't matter that you have a large particle somewhere. There's always going to be a crack, and it's a matter of making sure it doesn't grow by the failure of that protective oxide. So it becomes very specific, but I hope that you get the general idea. The general idea is you have a lot of failure modes from very high energy. The highest energy failure mode is when you flow the material. Everything going from there is a reduction in the total expense of energy, and that's why we have them. If you can inhibit all the slow cracking and the brittle fracture, you are in a situation where the behavior is the best, the most predictable. As soon as you get away from this very ductile behavior, it's difficult, because now it's not going to show signs of distress. It's only going to form little cracks, and if you don't have ways to detect them, you can have a sudden failure without any sign, pre-sign. You're also more sensitive. So if you're looking at a whole assembly, car is a good example. If I hit a bump on one corner on a car, a lot of times you have a little stretch, a little twist. It means in some of the connections, some of the weld, it will deform. You have plasticity. Well, if it turns out you made it out of a brittle steel, it's going to start to crack right there, even though overall you're not applying high loads, but you're just very sensitive. You're not forgiven about one or two overloads if you lose the ductility of your material. And that's the highest risk with embrittlement and cleavage. You can have one area, say one time, this is going to be almost like a tensile test. I'm pulling on it, and then I'm done. It gave me what I needed, gave me 1% strain, that's all I wanted. If your material can't give you 1 or 2% strain, most of the time it's not really considered structural material anymore. So that's kind of my pitch on that. So I hope it was a little easier than yesterday. I tried. Any comment I welcome, and questions, I have time here. So.